So we've already discussed RL electrical circuits. Now let's discuss chemical mixing. And it turns out that the behavior of these two systems is very similar. The governing equations are basically the same between these two systems as we pose the mixing problem. And again, this is section 2.3.4, and I'd also like to remind you to keep your objective of gaining an intuitive understanding between the simple systems and the equations that describe the systems as well as their behavior. That's what you're going to gain from this. So here we have, let's imagine we have a bath of fluid, and I'll just draw it as a simple, just like Greenberg does, as a rectangular tank. And it has an input valve and an output valve. And the input valve has a flux of fluid Q of T, and the fluid coming into the system has a concentration of a solute of C1. The output has the same flux Q of T. This is the so I'll go ahead and write that down later. So the same flux Q of T, and the concentration of the fluid coming out is the same as the concentration in the bath. So the concentration in the bath is C, and that's changing with time, and the bath has a volume V. So C is the concentration of a solute in the bath, and this is the quantity we're going to solve for. It's going to vary with time. And the bath has a volume V. Little v. Q is the in and out flux through the input and output valve. The flux being measured in, say, meters cubed per second. The concentration, say, is measured in grams per meter cubed or something. Grams of a solute per meter cubed of fluid. And C1 is our input fluid concentration. Okay, so this is our conceptual model of our mixing system. And so let's write an equation that describes the system. And this equation is conservation of mass of the solute, or it comes from the equation describing conservation of mass. So that is to say that the rate increase of the mass of the solute in the bath is equal to the rate added, the rate of mass added to the system through our input valve, plus the rate lost through the output valve. Okay, and so we can describe the rate increase in mass of the solute as dx dt, where x is the mass, and that's equal to the rate added, which is the flux of fluid added times the concentration of the added fluid. And then the rate lost is, well, minus Q of T times the concentration of the fluid leaving the bath out of the exit valve. And the concentration of T is related to the mass by, again, the mass over the volume of the fluid. So we can write that, we can change this conservation of mass equation into change this rate change in mass to a rate change in concentration. By just dividing both sides of the equation by V. So we have Q of T over V times C1 minus Q of T over volume times the concentration in the bath. And writing this equation, we have a time derivative. So we have a first order equation in terms of a time derivative of the concentration. And it's linear, again, because this is a linear function of the concentration and its first derivative. And it's non-homogeneous because we have a term that's independent of the concentration of the bath. It's only dependent on the flux of water into the bath and the concentration of fluid we're adding to the bath. So it's a linear non-homogeneous first order equation that we can write as C prime plus Q of T over V times C is equal to the right-hand side, which again is the term that is independent of C, the quantity we're solving for. So again, it's first order, linear, and it's non-homogeneous. And in fact, you might recognize that the form of this equation is the same as the form of our electrical circuit equation. So remember, we had the rate change in the current, or which I'll write as I prime, plus R over L, the coefficient on the current, which in this case was constant. In the above case, it could vary depending on the in and out flux. And the right-hand side in our electrical circuit was the voltage drop across our battery divided by our inductance term. And actually, we had the general equation had a time dependence on our battery voltage. So if let's say that our in and out flux was constant, so the valve drawing water in has a flux again equal to the valve letting fluid out, and that is constant over time. And so our ODE becomes C prime. I'm going to use white ink. So we have C prime plus our constant Q over V times C is equal to Q naught over V times C1. And drawing this is the same form of our RL circuit if our voltage was constant. So let's look at our solution for the concentration, and let's look at the particular case in which the initial concentration in our bath is 0. Right? So we have a bath, for example, filled with pure water, if water is our fluid, and we're dumping fluid with a non-zero concentration into our pure fluid, and then at the same time we're allowing some of that fluid to escape. And we're assuming that the bath is mixing perfectly so that the concentration is leaving the system is equal to the concentration in the bath. So when we start off at t equals 0. Again, our concentration is 0. At large time, as time goes to infinity, you can imagine that all the fluid that was initially in our bath will be completely replaced by the fluid that we're putting into our bath. So after a long time of this system running, you can imagine that the concentration in the bath will be C1. So the long-term solution is C1. And we'll have an exponential increase in the concentration from 0 to the concentration of our input fluid. So we started off with no solute in our bath, and we ended up with all our initial bath fluid being replaced with our input fluid with concentration C1. And from in between, from when we first start pouring we first start pouring fluid in and taking fluid out to our infinite time, for after a long time after the system is running, we have an exponential increase in the solute concentration in our bath with time. So this is another way to understand this solution through this system, very simple system of mixing when we're adding a fluid to a bath while that is perfectly mixed. So I will conclude this video here, and hopefully now you can see the similarity in solutions of the RL circuit and our chemical mixing. They describe very different systems, but the solutions are the same.